This is the first part in a two-part series on maximum and minimum values. In Chapter 3, largely what we've learned were derivative rules, and in Chapter 4, the main point is to study derivatives in order to study the graphs of functions, like what the shape of the function is and how big or small a particular y value gets. And this all leads up to a topic in section 4.7 called optimization. The basic idea of optimization is to answer a question of this kind. So you have a function, f of x, and then when is that y value the biggest? An optimization problem might look something like this. So you have to sell a certain number of CDs x, and then you have this function that gives you the profit. There's this thing called a constraint. In some real-life settings, the choice that you make is constrained by something, like in this case a contract obligation. The question that you're trying to answer is what x value do you have to pick so that the y value here would be biggest. Like in this particular picture, you'd pick this particular x value down here because this will give you the biggest y value. And that's the basic idea of optimization. In some settings you want y to be big, so like something like profit or the number of cookies, and in other settings you want to make y as small as possible, something like you want to reduce the amount of traffic. So here's a couple definitions. The ordered pair c comma f of c is a global maximum point if that y value is the biggest among all y values inside the domain of the function. Just the x coordinate is going to be called the global maximum x value, and the y coordinate, this f of c thing right here, is going to be called the global maximum y value. And you have analogous definitions for global minimum point and global minimum x value and global minimum y value. Collectively, these points are called the global extreme points. On an intuitive level, this is just asking what point on the graph is the tallest, what's the highest point on the graph. Imagine, what's that tallest peak or mountain. Like if you stood there, then no other piece of the graph would be a taller mountain that would obstruct your view. And then likewise, what's the shortest or bottommost point on the graph. So in this example, that's this point right here. 0, 1 is a global max point. That x coordinate 0 is a global max x value. 1 is a global max y value. And there is no global minimum point, because if you think that this point is the global minimum point, well, the y value here is -1. And then there's another point on the graph where the y value is -2. And then from here, you'd think, well, maybe this is the global minimum point, but then this point has a smaller y value, and then this point has a smaller y value, and it just keeps going like this. In the next example, you have a global minimum point along with the global min x and y values, and there's no global maximum point. In this particular example, you can see that there's this function levels off towards 0, so you have a global maximum point and a global minimum point. And this is sort of to contrast with the previous examples where you could have a global max point and no global min point. That was our first example. And the second example was the reverse way around. And this example is more typical in that you have both a global maximum point and a global minimum point. You could also have this situation where there's multiple global maximum points or multiple global minimum points. And this happens when you have tying y values in something like sine of x, which is periodic. This function has no global max point or global minimum point, because if this point you'd think would be a global max point, well, there's a place with a bigger y value and a place with a bigger y value. And similarly, if you think this point is a global minimum point, well, this spot has a smaller y value, and this point has a smaller y value, and this point has a smaller y value, and this point has a smaller y value, and so on. This graph also has no global max point or global min point. If you think that this is a global max point, the thing is, this point over here has a bigger y value, right? The y value here looks like it's about 1/2, and the y value here is 2. And then, just like in the previous example, you can keep arguing that there's no global maximum point and no global minimum point. But these little bumps right here, these are interesting, and we will talk about them a little bit later. Okay, this graph has 2 global maximum points. These bumps down here are not global minimum points, again for the same reason that this point over here has a smaller y value, and then this point has a smaller y value, and so on. And then this little bump right here is not a global maximum point. Okay, this does look like the outline of a cat, so I'll call this the cat function. Now, our basic goal is to try to make a recipe for finding global max points and min points. But graphing takes a long time, so it'd be nice to have a recipe that didn't involve graphing the function. And this is just to recall the definition. We saw this earlier. The book will use this terminology. The y value that I've called the global max y value is called the global maximum value, or the global maximum, or absolute maximum value, or absolute maximum. And instead of giving the x value, c here, a name, the book will use at as a preposition. Now, to contrast this definition, there's a thing called a local maximum point, where you change the for all x in the domain to all nearby x values, all x values which are near this x value of c, and you have all this analogous stuff. Okay, as far as these definitions go. On an intuitive level, a local max point is a place in the graph where a small helium balloon, when released, would go up to that point in the graph and the balloon would get stuck. And a local min point is, imagine falling rain. Where would rain collect in the graph? And these intuitive ideas are, of course, never quite capturing exactly what's going on, but they get the right idea across. To fix this a little bit, I should say that these things, these intuitive ideas, you should think of what happens on a slightly windy day. And this probably doesn't make a whole lot of sense right now, but we will look at an example in a second. So going back to this cat function, there are 3 local maximum points. If you get rid of a helium balloon right here, it will slide up to right there, and this is the spot where a balloon would get stuck. Over here, you'd let go of a balloon, it would slide up to right here, and it gets stuck here. These 2 points are local minimum points. Imagine rainwater falling down here, and water would collect right in this little dip and in this little dip right there. Okay, so these 2 points we saw earlier were global maximum points. This is not a global maximum point, but this is, so to speak, the 3rd local maximum point. Okay, what I do want to do is look at these 5 locations because there is something very interesting going on here, and that is that the slope of the tangent lines at all of these spots is 0. That means that the derivative is 0, and so this gives us something very interesting and useful to look at. To look for global maximums, this is not the right recipe yet. This is a preliminary recipe, but the idea should be just look at all the local mins and max points, and then look at the y values, and whichever y value is the biggest, that should be the global max, and where the y value is smallest, that should be the global min. So then you need a recipe for local mins and maxes, and based on that cat function we just looked at, the thing to do would be to look at x values, call them c for now, look at those x values c where f prime of c is equal to 0. Or in other words, find the derivative of the given function, set that derivative formula equal to 0, and solve for x. So let's do that in some examples. First off, just in the picture, this point right there is a spot where a balloon would get stuck, so this was previously a global maximum point. It still is, but it's also a local minimum point. Now, without paying attention to this graph at all, you could do the same thing algebraically by taking this function, take its derivative, set that formula negative 2x equal to 0, and the only solution to negative 2x equals 0 is x is equal to 0. Okay, so you still get this 0 right here. Okay, you discovered the same x value. And if you needed this y value, well, you plug in this 0 into the formula for the function. Next example, same idea. In the graph, there's a local minimum point, a place where water would collect is right there. And in order to discover the 0 without doing the long process of graphing, take the derivative of x squared minus 3, you get 2x. Set 2x equal to 0, the only solution is x is equal to 0. In this next one, there's a local max point and there's a local min point. A balloon gets stuck here, water gets stuck here, and if you want, there's some algebra. You use this fact to basically rewrite the function piecewise and then differentiate each of these individually using the quotient rule, and then set this formula and this formula each equal to 0, and you only solve this one for x values when x is positive, and this formula set equal to 0. Only care about solutions when x is negative. So let's just solve these on the next slide. Right here, just multiply to clear out the denominator, factor, and this e to the x is never equal to 0, so it's only this part, 5 minus 5x equals 0, has one solution. And then similarly, take the second equation on the previous slide, set that equal to 0, and factor, and the only solution is x is equal to negative 1. Go back to sine of x, that was an example we looked at. Here are local maximum points and local minimum points. These were also global max points and global min points. And to do this without graphing, well, you could take the derivative cosine of x, set that equal to 0. And the solution to cosine of x equals 0 is pi over 2 radians plus any multiple of pi. This function right here, earlier we saw that had no global max points or global min points. It also has no local max point or local min point. You might think that this point right here is a local maximum. You'd leave a balloon right here, and it would get stuck a little bit. And this now goes to that slightly windy day thing. So a balloon right here would end up, with a little bit of wind, end up being pushed right here, and then the balloon would slide up. So this is not a local maximum point, and likewise, rainwater might stay here just for a moment, but with a little bit of wind, the rain would fall down this way. So this point is not a local max point and not a local min point. If you do the calculus way, take the derivative here, set this equal to 0, you actually will get 0 as a solution. And so wait, that's not right, because 0 didn't correspond to a local max point or a local min point. And that seems to be a little problem. It's not really a problem. Basically, all we're going to do is just change the recipe a little bit, because we got that f prime was equal to 0, even though x is equal to 0 was not a local min point or a local max point. The recipe is basically the same. This is the same recipe as before, except we just add this little caution that sometimes you discover an x value that is not a local min or a local max, and that's okay. You know, that's just, you hold on to this x value, and well, so what? You have this extra information. So sometimes you set the derivative equal to 0, solve for x, and that x value is 1 you didn't want anyway, but that's not a big deal, because the overall recipe for global mins and maxes was to just take each of the x values, look at the y values, and all you wanted to do was find out what's the biggest y value and what's the smallest y value. And so if you get an extra x value, you just get an extra y value, and that's just an extra number in the list to compare. No big deal. Go back to this function. This function does have a local max point and a local min point. So right here, a balloon would get stuck, unlike in the previous example, even on a windy day. Now, it can't be too windy or a balloon would fly out here. So that's why there's slightly windy. Okay, and right here as well, water would collect right there. Okay, the next example is the function absolute value of x, and right here there is a local minimum point at this sharp corner in the graph. Rainwater would fall and get stuck right there. However, the thing is, if you tried to take the derivative, well, the derivative of this function is not defined at the x value of 0. So we need to update our recipe, because this local minimum right here was not found using our current local minimum finding recipe. Just as a review, f is differentiable if this limit exists, and sort of in a more intuitive way, you can look at the graph and see, is the graph smooth? And that's differentiable, and non-differentiable more or less means the graph is pointy or sharp, or turns a sharp corner quickly. And so the updated recipe is simply this. Don't only just look for x value c where f prime at that x value is equal to 0, but also look for when the derivative at that x value doesn't exist. It's basically just look at this extra spot, and that's about it. And we're just going to reword this on the next slide using this definition. So the x value c is a critical number for the function f if either f prime of c equals 0 or f prime of c does not exist. These are the two interesting cases we were looking at in the updated recipe for local mins and maxes. And now the recipe for local min and max point is very nice. It's just look for those c values, which are critical numbers according to this definition. But we still have this warning, as before, that such an x value does not have to correspond to a local min or max. And then if you want, you could say there's an updated global min or max point finding recipe, and what used to just say here, find the local mins and maxes, it still could, but now you could just say find all the critical numbers. And then this is as before, just for all those x values, get the y values, whichever is the biggest y value, that should correspond to the global max, whatever is the smallest y value should correspond to the global min. And this recipe is not quite right, so this recipe is in its final form, but this one we'll have to fix a little bit. We'll do that next time. One last example, how about this function here, 1/4 of absolute value of some quantity of absolute values in here too. And all these absolute values, what they end up doing is they create these sharp pointy corners in the graph. These are spots where the graph is not differentiable. So this graph looks sort of like the bottom part of the Batman logo, sort of, and it has 7 critical numbers. 6 of them are these pointy spots, 6 spots where the derivative doesn't exist, and then 1 spot right here where the slope is 0. That's where f prime is equal to 0. Okay, see you next time.